Just a minute, sir. Okay, now, sir, is it okay now? Is it okay now? Any Muruganandam?
Sir, okay, sir.
Okay,
Audible,
sir.
sir.
Okay, right.
Yeah,
Thank you.
okay. I'll share my screen.
Just a minute, sir. I will introduce you and then you can start your session, sir. Okay, today's speaker, Dr. B. Venkatesa Perumal, Professor and Professor in charge of NIT STEP, Department of Electrical and Electronics Engineering, NIT Karnataka, Surathkal. He is having uh, is working from working in NIT Surathkal from 2015 onwards, and in various capacities like associate professor, head of the department, professor, all these capacities, and he worked in industries, Sun Edition Energy, Bangalore, and APC India Private Limited, GE Healthcare, BPL Healthcare Bangalore, and he visited San Francisco and Japan for this product development. His qualification is concerned, he completed his electrical BE in Electrical and Electronics Engineering from University of Madras, and Masters in Power Electronics and Drives in Bharatdasan University, PhD in IIT Delhi, and in his credit, he has 7 patents granted, and he completed 17 crore R&D projects and published more than 20 papers in the reputed journals and 20 conference papers. And he completed his he guided PhD scholars, and 2 of them completed and 3 are ongoing. So it is, and he organized many national level and international level programs, and he received many awards. So if I am reading all those things, it takes another 10 to 15 minutes. So with this brief introduction, it is fortunate to have such an eminent personality with us for today's session. So on behalf of you and my own behalf, I welcome Dr. B. Venkatesa Perumal. I hand over the session to Dr. B. Venkatesa Perumal. Sir, please.
Yeah, thank you. Thanks for the brief introduction. Sorry if it is a background, if there is a noise, sorry for that. Okay, so because due to some emergency, I have come for some other meeting. So I'm sitting in airport, I'm talking. Sorry for that. So I hope my slide is visible, right?
Yes, sir. Your slide and
Yeah,
audio both are
okay.
clear, sir.
Thank you. Thank you. So I have 2 PPTs which I wanted to present it for this forum. So the first one is here. So if you see that, this is what my content which I am going to do, that introduction and chargers, what it is used in EV application, and it's a bidirectional and how it is connected with the grid side, and methodologies and results. And the other one is going to be with the solar, how it is connected. So basically people are talking about that hybrid vehicle. So just I would like to say that this is the configuration which I have taken it from the internet, but there is a mistake in the second figure and the middle one and the first one. So if you see that hybrid electric vehicle, so you have a IC engine connected with the system rear wheel, and the front wheel, and then it is connected to the motoring system also, basic starting mechanism. That itself the people talks tell about that it's a hybrid system. The second one is, if you see that the plug-in hybrid electric vehicle, so basically there will be a battery and also a diesel engine. There is no connectivity in the braking side and other things. So basically it will be more, it will have more battery to operate, and also it will be operating with the diesel engine. or whatever the fuel engines, whatever it is connected. It's in the hybrid mode, it will operate it in this. Plug-in hybrid is basically we are charging it from the external. The battery need to be charged from external side. The third one is completely, it is a battery vehicle, battery operated vehicle. So there is no IC engine at all. So the basically the system efficiency, overall system efficiency, if you look at it with the given figure, if you look at it, the first one will come around 30 to 35 percentage. The second one will be improved upon on that. But the last one is the efficiency point of view. It is a very, very higher one. Now, the same thing which I have shown in this different figures. So the electric vehicle and hybrid electric vehicle, plug-in electric vehicle, what kind of a things? It's a mild electric vehicle. So that is also a part of the system. You can see that the battery pack size, how much it is required for only EV requirement. It's a 20 to 80 kilowatt hour requirement is there. But if it is a hybrid mode, it is the battery size is coming down. So basically the compensation is done with the induction in the IC engine, how it has been replaced and what kind of a things it is happening over there. So plug-in one, it is basically a hybrid, but the battery can be charged with the outside. And mild hybrid, again, it is going to be in a different configuration. But most of the cases, the electric vehicles are classified in this category and the charges are in this range. So the other impact, what it happens with the grid connected system, if you see that this is called, it's a duck curve, people would have come across. So you can see that our normal load profile in daytime, when early morning it starts, that the load is goes up and it is stays over there for entire day. And the evening hours that the curve goes and hits into the top and it comes back. So what we worked on this particular charger, because this market is coming up and electric vehicle is also started getting matured enough to get that more number of vehicles. So what we thought about is penetration of the renewable sources to the grid, and to address the duck curve, vehicle to vehicle charging or vehicle to grid, these kind of things, options we thought about it. With that configuration, it has come. So this is a converter topology wherein you can charge the battery, or from the battery to grid you can push it. So here we are not talked about anything on the solar aspects. So here basically it is a converter topology. If you see that the bridge converter followed with the full bridge converter followed with this LC filter, again it is rectified. So it's a DC to DC converter. The output of that one, it is connected with the capacitor and it is given to that inverter, single phase inverter, and pushing back into the grid. So through that, this, if you cut the portion, if I talk about that, the portion what you are talking about here, the uh, thing is, when you see the bridge circuit, it is operating as a single phase bridge inverter. Basically, you can say that it's a grid tie inverter. In case if you want to see that power, so here the power what, just once again. So basically that power what I wanted to mm, transfer from one end to another end, the battery power, it goes from the battery to converter, DC to DC converter, it goes to that rectified again in the secondary side. Now you can see that switch number 5 and 6, front end switch 1 to switch 4, and followed with 6 for switch number 6, S5 and S6. It goes to that the DC capacitor, DC link capacitor. If you would have come across with any of the grid tie inverter, PV based grid tie inverter, so this is the same structure which is pushing the power to grid. That is what the configuration we worked out. So you can see that the power flow, if I operated these S1 and S4, S3 and S2 in a different direction, so the high frequency transformer is used. So we will get that high power density. That's why we used that one and boosting the power. Now, to get that 230-volt output in the RMS, we need at least a minimum 400 volt at the DC bus side. So the voltage at the DC bus, if it is a fixed at 400, depends upon that DC battery voltage. You can think of that the saying that 48 volt if I have a battery. The 48 volt battery need to be charging the capacitor up to 400 volt whenever it is in pushing the power to grid. So according to that, the control need to be done. The power flow from this battery to grid, it's nothing but the battery used in a electric vehicle. That battery is discharging to the grid. When it has to happen, if you see that the curve, this is the time where the peak, it is happens from the 6 o'clock to that 8 o'clock, the sharp rise in the load demand and it goes. So during this time, if the car is parked at your home, if the office hours are over at 5 o'clock, from 6 o'clock to 8 o'clock, if you see there is a peak rise and then it comes back. So during this time, if the cars are parked in the parking lot, can support the grid, so that my grid demand is going to be flattened over here and support that additional load. So that is the condition wherein we want the power flow happens from the DC battery to the grid. So when we want to do that, first thing is, one is, if I am taking it out, the circuit, whatever it is there, this circuit, if I say the charger, one is a charger, another one is pushing into the inverter. What is the condition it be? If I at all, if I am using a grid tie inverter, the grid tie inverter need to be satisfied that IEEE 1547 UL of UL 14 number, those standard it has to meet. So if that is the first case, if it is an onboard charger, it is available. Only AC plug kit is available. If it is an off-board charger, we no need to worry about any automotive component standards. But if it is an onboard charger, basically the charger is placed inside the car itself. It is an onboard charger. Only AC plug card is available. Under that condition, you have to make sure that the entire component is meeting that the automotive grade component. What is that meaning of automotive component? Is automotive grade component, it has to work from -50 degree to 150 degree centigrade temperature. So the each and every component should be selected in such a way that so the power flow can be done for onboard charger. If it is an off-board charger, only the grid tie inverter requirement, whatever it is there, that has to be taken care. At the same time, when it is charging, the charging standards, which is which may not be equivalent to that component of automotive grade, but at least this will be the industrial grade ones. So the power flow is happens in this way, and we have to do the analysis. Now you can see that during the positive half cycle, we have put that switches S1 and S1 and S4 is turned on during that positive half cycle. The top side, and I'm not using that the S6 and S4, both the switches are not operated when the power flow from vehicle to grid mode. So I'm turning on the duty cycle for this particular switches need to be kept constant below 0.5 in theoretical case, but in case of practical, we used to keep it at that 0.45 is the duty cycle, because shoot through to avoid the shoot through fault. Now this is in the first case, during the first positive half cycle, it has been positive half cycle, it has been positive half cycle. This has been um, uh, So this has been, you can see that during the positive half cycle, the flow goes in this way and rectified, and it is charging that. During the negative half cycle, it goes into the current in the transformer is reversed. At the same time, the current flow through the capacitor is in the same direction. Now you can see that both the cases, whatever the voltage is there in the DC, has to be amplified and it has to go to that 400 volt. Now I said that wherein I want to use that system to be in a amplifying mode, the turns ratio, which I will make sure that the turns ratio is always meeting that the 400 volt requirement. At 0.45 is my maximum duty cycle condition, and duty cycle condition with the maximum load load point. Just I'm doing that. Just a moment. I'm changing my uh, yeah, sorry. So this particular one. So basically during that negative half cycle, we are charging in a 400 volt, it is going to the system. So in this case, the power is transferred from DC battery to the capacitor, and the capacitor, from the capacitor we can evacuate the charges to the grid side by using the another control. Now the other side of operation, when we wanted to do grid to vehicle mode, what it happens is basically for your S5 and S6 is operated. Now the diode is not operated in this particular case. So based on my duty cycle, which I said that the 0.45 is a duty cycle, which will deliver the maximum load to the system, maximum power what you are designing at this particular duration. Because even though we are trying to control the voltage, at the end of the day, the system what it is going to control is the 400 volt maintenance will be taken care by the inverter control, and the full bridge converter will always operate it in a current control mode, so that the maximum current, how much ever it is possible, it will deliver according to that load. Because if the voltage is going beyond that 400, immediately I need to control my duty cycle. If the power input, whatever I am taking it from the battery, it is not pushed, it is not able to push into the grid. That means it is already reached the maximum. So under that condition, my duty cycles will be always is a positive condition. If the duty cycle will vary and make it that the power flow to happen. Here, in this case, the grid to vehicle mode. So why we need this particular case? When the after that 8 or 10 o'clock, again that the load pattern is coming down, so making it the system to be in the constant line. My aim on this particular slide is, you see that the load line on the grid, if I make it straight, my system is going to be stable, and also I will get economic operation of the all the generators which is connected into the grid. It will also get benefit. We know that the losses can be minimized if I operate it with the optimum condition. So that is nothing but if I operate it, the load line, it is always a constant. Now you can see here, in this case, we are supported by the vehicle to grid. After this point, what I'm going to do is the charge the battery through the grid to vehicle. So under this condition, we can see that the voltage current profile, how it is happening in the positive cycle So S6 is on, the center tap one it is on, so the completing path. And in case if the both the switches are on, what it is going to happen? It will get cancel each other because these two voltages are opposite to the supply, and then it is going to cancel each other. We will get the zero. So the effective voltage can be varied by phase modulation even in this case. So only S6 is on, you can get the full voltage into the system. You can see here the S1 is on, S5 is on, and S6 is on. Whenever these two are on, what is the voltage across the output you are getting? Because this winding one and the winding DC link voltage and the inductor voltage, which is going to the maximum, when the S1 is on, the voltage V1, V2, and the total voltage, if the both the switches are on, you can see that the voltage across this one is zero, and both the switches are any one of the switches operated, you can see that the waveform is going into the as per the discharging curve which is there in the positive side and negative side. So this overlap period, if you control, you can control the output voltage magnitude. According to that, basically the power flow from the one system to another system. So coming to the grid side converter, when the grid side converter, the power transferred from the 400 volt to that the for DC bus to that the load, basically here load is nothing but my grid system. So the capacitor is start.
Your voice is not clear, sir. It's a connection.
Just once again. Once again. Sorry. Yeah. So this is the slide where I got stuck. So this is basically here the power is transferred from the 400 volt DC bus to the grid side when it is connected to the system. So now if you see that the basically this is during the positive half cycle, your power is going to be pushed from the 400 volt bus to the grid side. Now, during this negative half cycle, you can see that negative half cycle, how that the other two switches where it is turned on and how it is connected. You can see from here in this case. So when the two switches are in on condition, how the power flow is happening, positive half cycle, negative half cycle. When it is a negative half cycle, how the power flow will happen? During the negative half cycle, the V2 vehicle to grid, positive half cycle of the grid, what it will happen even if I turn on these two switches, the diode will come into the picture and it will allow that the circulating path. That is what we wanted to mention over here.
Your voice is not audible, sir.
And when the power supplied from this in this case, you can see that